Hello students and welcome to the new lecture session of Acoustic Emission Testing. Myself Shankar Ghosh, Assistant Professor of Automobile Engineering Department at Dr. Sudhir Chandra Sur Degree Engineering College under the JIS group. Today we will discuss on acoustic emission testing. This is the module number 8 of non-destructive testing and the application. This is the 7th semester syllabus of automobile engineering students. So, in the objective of today's class is to understand about the acoustic emission testing by its definition, then going through its basic principle, historical aspects, basic principle, then we will go through its instrumentation and its empirical relation. So, and the outcome of today's class is that students you can easily define the acoustic emission testing. You can easily understand about the history or Kaiser Effect. You can understand the working principle and the instrumentation methods of this testing, and finally you can find out a relationship which helps this acoustic emission testing. So student, let's start today's class that on the topics of acoustic emission testing. Acoustic emission testing. Students, whenever we tear a paper, break a twig or chop, bend or unbend a tin sheet of foil, crack a timber or a light, we do hear the tearing or breaking process. We do hear the tearing and breaking process. In other words, acoustic sound energy which is released in this process. Now sound is a form of energy. Sound is a form of energy, and we all know that sound is a form of energy, and we all know that energy cannot be produced or destroyed. So we can only convert one form of energy into another form of energy. So hence one should wonder as to which form of energy is getting transformed into the acoustic energy in this tearing or the breaking process. It is sometimes like this. Every material has stored elastic energy within the volume of the material, and it is stored elastic energy that gets released in form of the acoustic energy whenever material undergoes a plastic deformation phase, transformation or fracture. So student, AE or acoustic emission arises due to stress wave generated by mechanical deformation of a material, and it is the detection and analysis of this stress wave at the surface of the structure that gives rise to the AE techniques. Traditionally, AE level is as a NDT or non-destructive testing technique, but it has actually found more success as a health monitoring tool. In static structural monitoring, in static structural monitoring of airframe, for example, AE or acoustic emission is essentially used as a large scale of strain gauge. In continuous monitoring of bridge structure, it is used to detect, identify, locate, and quantify the variety of damage mechanism. The recorded AE signal from a discrete or burst type emission can be summarized. The recorded AE signal from a discrete or burst type emission can be summarized by a number of basic parameters: peak signal amplitude, rise time, average frequency, ring down count, and the energy. Most of these complex functions of the frequency response of the sensor and damping characteristics of the sensor and propagation medium. Damping characteristics of this sensor and the propagation medium, coupling efficiency, sensor sensitivity, amplifier gain, and threshold voltage. In the past, acoustic emission systems were only able to record this parameter known as the AE feature data and not the whole waveforms throughout a test. So analysis techniques were just limited. The waveform parameters, however, provide a good indication of the intensity or severity of any AE source, and this information can be used to determine whether the structure under test is accumulating damage. So student, in short, the acoustic emission may be defined as elastic wave spontaneously generated electric wave spontaneously generated due to the release of stored elastic energy of the material as it undergoes plastic deformation, phase transformation, or the fracture. So this is the definition of the acoustic emission. Next is history. Sound and stress wave. Sound and the stress wave which is generated in various materials have been noted in the past for the several years. The scientist Joseph Kaiser was the first. Scientist Joseph Kaiser was the first to detect and systematically process the signal sound. Detect and systematically process the signal sound produced by the deformation of certain metal and process the slight sound and produced by the deformation of a certain material such as zinc, steel, copper and lead. This is the history of this AE testing or acoustic emission testing. Next is Kaiser effect. One of the observation made by the scientist Joseph Kaiser was the acoustic emission phenomenon. Acoustic emission phenomenon, which is irreversible. That is, acoustic emissions are not generated. During the reloading of a material until the new stress level exceeds its previous stress level value. So this phenomenon is widely referred to in the literature as the Kaiser effect. Researchers in the field of acoustic emission acoustic emission, however, express some doubt to the general validity of Kaiser effect. Especially for less homogeneous and anisotropic material, such as unidirectional fiber reinforced plastic composites. Also, in case of fatigue and the fracture, during the later stages of crack propagation, growth, plastic deformation continue without any further increases in the applied load, and acoustic emissions continue. Hence, the Kaiser effect is not operative in case of similar situation. The author also tried to verify the validity of the Kaiser effect, and for this purpose, a number of carbon fiber reinforced plastic composite specimens were tested using the acoustic emission testing technique. It was observed and confirmed that the Kaiser effect was not fully operative. Repeat of the tests invariably gave a lower count but not zero count. Repeat of this test invariably gave a lower count but not zero count, as would be expected in Kaiser effect was fully operative. On further investigation, it was noticed that the Kaiser effect violation might be because insufficient time and may have been permitted for all the counts to appear. So what are the effects? The material emits many pulses of elastic energy. Material emits many pulses of elastic energy when placed under stress. Once a given load was applied, and the acoustic emission from that noise had ceased, the further emission would occur until the previous stress level was exceeded. Even if the load was removed and later reapplied. The acoustic emission testing methods where the material being inspected which is generates the signal that one of impending failure. Solid material emit sonic and the ultrasonic acoustic emission when they are mechanically or thermally stressed to the point where deformation or the fractures occur. During the plastic deformation, dislocations move through the material's crystal lattice structure producing low amplitude AE signal, which can be measured only over the short distances under the laboratory condition. So, if the load were held until all the acoustic emission emanating from the sample undergoes loading schedule top, and only thereafter we unload and reload the sample, emission would not occur until the previous attained loaded is exceeded. But if load is not held at the same level for sufficiently long duration and without giving sufficient opportunity for all the count to surface, and we decided to go for unloading and the reloading. Emissions which did not get sufficient opportunity to surface would occur at a load that is lower than the one which was attained previously. This phenomenon is generally referred as the modified Kaiser effect or Felicity effect. The ratio of load at which emission reoccur compared to the previously attained maximum load is referred to as Felicity ratio or the Felicity percentage. The Felicity ratio is usually indicative to the amount of the damage, that was scraped into the material due to the loading schedule being followed. So these are the Kaiser effects. Now we will discuss about the principle. An acoustic emission source generates an expanding spherical wave packet. Which is similar to the one that we observe when we throw a small pebble in the converter of the pond. When these spherical waves reach the body or boundary or the surface of the material under test, a surface wave pocket is created, as shown in the figure. These surface waves are either relief or the lamp wave time. A piezoelectric acoustic emission. A piezoelectric acoustic emission transistor attached to the surface. Sorry. A piezoelectric acoustic emission. A piezoelectric acoustic emission transducer attached to the surface of the body and pick up this surface wave. The detection of emitting source. The detection of the emitting source, that is detection of defect flow from anywhere of the surface, allow a higher degree of freedom. It allows a higher degree of freedom for detecting the defect from a distance, and therefore the acoustic emission techniques becomes very useful for flow monitoring. Therefore, acoustic emission techniques becomes very useful for the flow monitoring of flows which are located at inaccessible place, and also for real-time monitoring. Other NED techniques such as pulse echo ultrasonic technique require that the probe be right on the top of the internal defect, and it may not be possible if the defects happen to the locate at an inaccessible place, or if the defects happen to the located at the place at which the top surface contour is neither wavy or very complex for the probe to sit over the same. Presence of a defect The presence of a defect can be evaluated using by a single transducer. However, for the linear location, we have to go for two transducers, and for determination of all the three coordinates, that is x, y and z axis, for pinpointing the exact location that exact location of the defect, one has to use the three transducer. Associated with this acoustic emission testing technique, is a parameter which is called emission count or ring down count. The acoustic emission count is a weighted measure of acoustic emission activity which occurs in a given period of time. So students, these are the principles of this AE testing. Next is instrumentation. The instrumentation used for acoustic emission studies ranges from single channel system to the sophisticated multi-channel structure location system using the computer and the visual display. The block diagram representing the basic unit of the acoustic emission testing equipment will be shown in this picture. Basically, the detection system has a transducer which is attached to the specimen. If the emissions from the specimen are emissions from the specimen are of higher magnitude than the prefixed threshold, a transducer picks them out. This received signal is then amplified and read as an acoustic emission count. The response of the system depends upon the amplifier gain setting used and the number as well as amplitude of the pulse being monitored by the transducer. Using a totalizer, the count rate is integrated to give the cumulative emission count. Count. The acoustic emission transducer. The acoustic emission transducer converts stress wave to a low level and high impedance. Low level and high impedance electrical signal. These signals are then routed. Routed to an amplifier, which is a total amplification can be up to 100 decibel. Through a preamplifier and the appropriate filter. The function of preamplifier is of twofold. First, to amplify the signal to eliminate environmental disturbances, and second, to convert the signal into the low impedance signal for transmission over the long distance. Filters are used. Filters are used to eliminate mechanical means low frequency and the electromagnetic noise. Use of band pass filters allows the choice of an operating frequency range. Generally which is in between 100 kilowatts to the 3 megahertz. An acoustic emission signal are characterized by their broad bandwidth, spectrum. The amplified signal from the amplifier then passes through a threshold detector, which picks only those signals which are of higher magnitude than a prefix threshold voltage. Using a totalizer, individual threshold crossing can be summed up to provide cumulative ring down count. One may use stiff chart recorder and the oscilloscope also as addition to totalizer unit or as stand-alone system for interpreting acoustic emission data. Sometimes a digital to analog converter is also used to obtain DC voltage which is proportional to the number of counts for display on the XY plotter. The acoustic emission data can then be plotted. Directly as the function of other test parameters. Several other accessories such as the audio amplifier, digital printer, analog, taper, recorder, etc. can also be included. So, students, these are the basic instrumentation of the AE testing or acoustic emission testing. Next one is empirical relationship. The instrumentation used for For the acoustic emission, it gives us some sum of acoustic counts. It gives some acoustic counts, which is the sum of the sum of acoustic count. The summation of the acoustic counts is known as the summation of acoustic counts is known as cumulative acoustic emission count and is usually written by which is usually written by this summation of AE. So student, the summation of acoustic counts, which is known as the cumulative account, known as cumulative acoustic emission count, which is denoted by this summation of AE, and this cumulative acoustic emission count is a function of applied stress and relationship between them when given in this equation. That is, the summation of AE equals to A into k to the power m, where, as I told, summation of AE equals the total cumulative acoustic emission during the test. A is the proportionality constant, and K is the applied stress intensity. K is the applied stress intensity, and M is the empirically derived exponent. Also, this cumulative acoustic emission count, when associated with the formulation of plastic zone at a crack tip. This accumulative acoustic emission count, when associated with the formation of plastic zone at a crack tip, it looks like the equation of this: Vp equals to B into summation of AE, where Vp is the volume of plastically deformed material, where B is the proportionality constant. Sometimes researcher used a parameter B. Which has a unique value as long as the single type, of emission source predominates. If the energy of emission events are randomly distributed, statistical analysis shows that a plot of number of emission, that is NA, exceeding a given amplitude level A is generally in form of this equation, that is NA is equals to A by A naught to the power minus B, where A naught is a constant and exponential B, that is the power B, is a material constant. A logarithmic plot of the cumulative distribution, the cumulative distribution would thus be a straight line of negative slope, which is equal to the B. In the loading of simple material, a large value of B from the acoustic emission amplitude spectrum indicates the emission from a large number of small events, whereas a small value of B shows the preponderance of high energy events. Size effects are eliminated because the value of B is not affected by attenuation of sound in the material, provided that all the amplitude are equally attenuated. In fiber composite, where several types of the source events occur, a single value of B is generally not obtained. So, however, in critical point of this amplitude spectrum may be identified by discontinuation in the plot of the B plot. So, this is the empirical relation in between acoustic emission techniques in the acoustic emission techniques. Next is source of AE. The source of AE is generated. The source of AE is generated by stress waves within a material. There is multitude of source of AE. In fatigue crack monitoring, for example, this can be divided into two groups. One is primary and second is the second one is secondary. In the primary, AE is related to a fatigue crack. AE is related to a fatigue crack growth and fracture mechanism parameter, and secondary AE comprises all other sources whether related to the presence of crack or not. The primary AE sources include cleavage, inclusions, microfracture and ductile tearing. The secondary AE associated with the fatigue cracks arise from the crack closure process, that is the fretting and debris grinding between the crack faces. And secondary AE is often important in detecting the development of crack. In fact, the most practical situation is mainly this secondary AE, which is readily detected, but it should be noted that environmental conditions strongly affect closer to the AE. A number of practitioners have attempted to relate some function of AE to the fracture mechanism of the fatigue crack source. A comprehensive review of which is presented by moving. So, class, in today's class, we covered the definition of acoustic emission testing, its history. We can covered the Kaiser effects, the basic principle of these techniques, instrumentation of these techniques, some relationship and means empirical relation of this testing, and we can also we study the source of the A. So students, this is the today's class, and next of this class, in the next class we will discuss the second part of this AE or acoustic emission testing. So till then, stay at home and stay safe. Thank you. Thank you so much.